Albert Einstein was the smartest man alive, and a Nobel winner just proved he was wrong about reality itself. A particle has no color until you look at it. Two specks can link across the whole sky and answer as one, faster than light. We'll follow the basement test that shook physics, the starlight that sealed it, and the strange truth it leaves behind. Like and subscribe if your mind loves this stuff. Let's begin. Albert Einstein spent the last 30 years of his life trying to prove the universe made sense, and he lost. You know his face, the wild hair, the chalkboard full of symbols. He cracked open time itself, showed that fast clocks tick slower, and that gravity bends light like a lens. For a while, it felt like Einstein could explain anything. Then came one idea he could not swallow. Other scientists told him something strange about the tiniest pieces of the world. They said a particle has no fixed traits until you measure it. They said two particles could link up and share answers across any distance, in a single instant. Einstein heard this and shook his head. To him, that sounded like madness. He believed the world was solid. He believed a thing is what it is, whether you watch it or not. The moon is up there even when you close your eyes, right? That felt obvious. That felt like the floor under everyone's feet. So Einstein went to war with the strangest idea in science. He wrote papers. He invented clever traps to expose it. He spent decades trying to show that the new physics was missing some hidden piece, a secret that would make reality normal again. He had good company on his side. Common sense was on his side. The whole history of human thinking was on his side, and he was wrong. In the year 2022, 3 scientists stood in Stockholm and accepted the Nobel Prize in physics. Their work did one thing above all. It proved, with cold machines and careful numbers, that Einstein's view of reality was false. The universe really is as weird as he feared, maybe weirder. Here is the part that makes people dizzy. We are talking about the smartest human most of us can name, a man whose name means genius. And reality turned out to be stranger than even he could accept. So, what did these 3 scientists actually catch the universe doing? They watched tiny flecks of light behave in a way that breaks the 2 rules you live by every day. 2 rules so basic you never even think about them. You will, after this. The first rule says an object has real traits even when nobody looks. The second rule says nothing can reach out and touch something far away faster than light can travel. Both rules feel like solid ground. Both feel impossible to break. The experiments broke them anyway. To understand how, we have to go back almost 100 years to a fight between 2 of the greatest minds who ever lived. One of them was Einstein. The other told him, to his face, that he was wrong about how the world works. That fight took 50 years to settle. It took a basement, a strange glowing machine, and a young man who secretly wanted Einstein to win. But before any of that, we need to understand the first rule the universe loves to break. The rule about whether things are even real when you turn your back, because the answer is not what you think. Look at something near you right now. A wall, a hand, the sky. It has a color. It has a shape. It sits there, being itself. Whether or not anyone watches, that feeling has a name in physics. Scientists call it being real. A real object carries its traits with it, like a backpack. The color is in the object. The size is in the object. You do not create those traits by looking. You just find them already there. This is the most obvious idea in the world. A baseball is round before you see it. Your phone is black in your pocket, in the dark, with the screen off. Of course it is. Einstein believed this with his whole heart. He once asked a friend, almost angrily, whether the moon stops existing when nobody looks at it. The question sounds silly. That was his point. He thought the new physics led to silly places. Now here is where your skin starts to crawl. The tiniest pieces of the world do not seem to play by this rule. A single particle of light, called a photon, does not appear to carry a fixed color or a fixed direction while no one checks. Before you measure it, The particle sits in a foggy, maybe. It holds many possible answers at once, like a coin spinning in the air, neither heads nor tails. Then you measure it. The fog snaps into one answer, heads or tails. One real result, pulled out of a cloud of maybes. Picture a vending machine with no snack inside until you press a button. Press button A, and a bag of chips appears, as if it was always there. Press button B instead, and a candy bar appears, as if that was always there. The machine seems to decide what is inside at the exact moment you choose. Before you press, there is nothing solid in there at all, just possibility. That is the claim that drove Einstein up the wall. It says the trait forms during the measurement, instead of waiting inside the whole time. If that is true for one tiny photon, it should be true for everything made of particles, which is to say everything. Your chair, your bones, the moon, all of it built from pieces that, deep down, hold no fixed traits until something checks. Einstein refused to believe it. He thought there had to be a trick. He thought the particle did carry a real answer all along, hidden in some part too small for our machines to see. A secret slip of paper inside the vending machine, telling it what to drop. For a long time, nobody could test who was right. The argument lived only on paper and in late-night debates. You cannot weigh an idea. You cannot put common sense on a scale. That is what made this fight so painful. Both sides sounded reasonable. Both sides used the same math. They just disagreed about what the math was telling them about reality. But the first rule was only half the storm. There was a second rule, and breaking it scared Einstein even more, because this one let two particles whisper across the entire universe, faster than light itself. Throw a rock at a window. The rock flies across the room, then the glass shatters. First the cause, then the effect, with a little trip in between. Every event you have ever seen works like that. Something has to travel from here to there. A push, a sound, a beam of light. Nothing reaches out and changes a faraway thing with zero time passing. There is always a gap, always a journey. Scientists call this rule being local. Local means the world is touchy. To affect something, you have to reach it. You have to send a signal, and that signal needs time to cross the space between. And there is a hard speed limit on all of it. Light. Light is the fastest thing in existence, and even light is not instant. Sunlight takes about 8 minutes to cross the gap from the sun to your face. The sun could blink out, and you would keep feeling warm for 8 more minutes, because the news of its death has to travel to you at light speed. Nothing beats that limit. Not a rocket, not a radio wave, not a text message. This is one of the deepest laws Einstein ever found. Information cannot jump across space faster than light. Reach out all you want. You still have to wait for the message to arrive. So now put the two rules side by side, because together they feel like solid ground. Rule 1. Things are real. They carry their traits whether or not you look. Rule 2. Things are local. Nothing touches a distant object faster than light can fly there. Almost everyone who has ever lived would bet their life on both. They match everything you see, every single day. They are the quiet floor your whole world stands on. Einstein wanted reality to obey both rules at once. Solid things, a fair speed limit, no funny business. He called this the reasonable view, and honestly, it sounds reasonable. Here is the trap the universe set. The strange new physics said you might not get to keep both rules. Something in the tiny world was breaking the floor. Certain particles seemed to ignore the speed limit completely, as if the space between them did not exist. Einstein was sure there had to be a normal explanation hiding underneath, a trick, a secret the particles carried from the start. To prove it, he sat down with two younger scientists and wrote one of the most famous papers in all of science. And it started a fight that would last 50 years, a fight he would not live to see finish. Seal 2 coins in 2 boxes. Send 1 box across the country. Keep the other on your desk. You and a friend will open them at the same moment. Now, if these were normal coins, The story is boring. Maybe someone set one to heads and one to tails before sealing them. You open yours, see heads, and you instantly know your friend has tails. No magic. The answers were decided long ago, hiding in the boxes the whole time. That is exactly the explanation Einstein loved. Boring is good. Boring makes sense. Some particles refuse to be boring. Scientists learn to make pairs of particles that are deeply linked. The fancy word is entangled. When two particles are entangled, they behave like one connected thing, even after you pull them far apart. Now the strange part. Each particle, on its own, gives a totally random answer when you measure it. Heads or tails, 50-50, no pattern. You truly cannot predict your own result. It is as random as a coin you have never flipped. And yet, when you and your friend compare notes later, your random answers match every single time in a perfect mirror. You got heads, your friend got tails. You got tails, your friend got heads. Always opposite, always in sync. Two coins that are each pure chance, but somehow always agree on the answer. That should be impossible. Now stretch the distance. Put your friend on the far side of the country, almost 3,000 miles away. The trip from New York to Los Angeles. The matching still holds, instantly. Put your friend on the moon. Still holds. Point one particle at a star across the galaxy. As far as the math says, still holds, with no delay at all. The link holds no matter the distance. It acts in the same instant, and it slips past every detector we own, leaving no signal behind. The two particles just act like a single object smeared across a huge gap. Think of two dancers who have never agreed on a routine. You put them in separate buildings with no phones, no windows, no way to talk. Music starts in both rooms, and they move in perfect mirror, every step matched, as if one mind controlled both bodies. You would search the rooms for a hidden wire. You would be sure someone was cheating. That is exactly what Einstein did. He searched for the hidden wire. He was certain the particles were cheating, carrying secret answers all along, just like coins set before sealing. But the new physics insisted there was no secret answer inside. It said each particle stayed a foggy, maybe until the moment of measuring. And only when one was measured did both snap into matching results at the same instant across any distance. If that were true, the two coins were not following a plan made in advance. They were somehow deciding together, faster than light could ever carry the news between them. Einstein could not stand it. To him, faster than light meant impossible. It threatened the deepest law he had ever written. So he set out to kill the idea, in print, with the sharpest argument of his life. He thought he had found the flaw that would bring the whole strange theory crashing down. He had no idea he was about to lose. In the year 1935, Einstein and two younger partners published 4 short pages that shook physics. Their names were Boris Podolsky and Nathan Rosen. The three of them worked at a research center in New Jersey, and they were furious at where the new physics was heading. So they built a thought trap, a puzzle on paper meant to expose the madness. The puzzle went like this. Take an entangled pair, send the two particles far apart. Now measure one of them. The instant you do, you learn something certain about the other one, far away, without ever touching it. Here is their knockout punch. If you can learn a real fact about the faraway particle without disturbing it, then that fact must have been real all along. It must have been sitting inside the particle, waiting, a genuine trait, carried from the start. In other words, the particle had a secret answer the whole time, and if the new physics could not see that secret answer, then the new physics was missing something. It was incomplete, a half-finished map of reality. That was the argument. Sharp, clean, and signed by the most famous scientist on Earth. Einstein had a nickname for the alternative, the idea that the particles really did decide together across the gap. He called it spooky action at a distance. He meant it as mockery. To him, anything that worked faster than light belonged in a ghost story, not a physics paper. Picture two friends being questioned by police in separate rooms. They never planned their answers. They cannot hear each other. Yet every reply lines up perfectly, again and again. A normal detective would say they must have agreed on a story beforehand. That is the only sane explanation. That hidden agreement, made in advance, is what Einstein swore the particles must carry. His paper landed like a bomb. People still talk about it, almost 90 years later. It is one of the most cited science papers ever written. Students learn it by the initials of the three authors, a little code stamped into history. And for a moment, it looked like Einstein had won by pure logic. His argument was hard to escape. Either the particles carried secret answers, which meant the new physics was incomplete, or the world allowed spooky links faster than light, which felt insane. Most scientists quietly agreed with Einstein and moved on. He was the genius. After all, who would bet against him? One man took the bet. He was a short, intense physicist working in Denmark, and he had spent years arguing with Einstein face to face. He read the famous paper and refused to accept the trap. He believed the strange new physics was telling the truth about reality, spooky parts and all. His name was Niels Bohr, and he was about to fire back at the most respected mind in the world and tell him politely but firmly that he had it backwards. The fight between these two men would split physics down the middle. Colleagues picked sides, friendships strained, and for 30 years, nobody on Earth could prove who was right, because the argument lived only on paper. There was no machine yet that could ask the universe directly. Someone would have to build one. Niels Bohr was the one man alive who could stand toe-to-toe with Einstein, and he did it for decades. Bohr ran a famous physics center in Copenhagen, Denmark. Young geniuses traveled from all over the world to argue in his rooms. He was slow, careful, and stubborn. He would chew on a single sentence for hours. Where Einstein was quick and clear, Bohr was foggy and deep. They could not have been more different. The two men had been arguing for years before the famous paper. At science meetings, they would go at it like prize fighters. Einstein would invent a clever puzzle over breakfast, sure he had finally trapped the new physics. By dinner, Bohr would have torn it apart. Then Einstein would build a new puzzle overnight, and the dance would start again. When Einstein's spooky action paper landed, Bohr dropped everything. People who were there said he became obsessed, pacing, muttering, unable to think about anything else. He knew this attack was the most dangerous one yet. Then he answered. Bohr's reply flipped the whole question. Einstein had assumed a particle must carry real, separate traits, sitting inside it, waiting to be found. Bohr said that assumption was the mistake. He claimed a tiny particle owns no fixed trait until it is measured. The trait and the measurement are tangled together. You cannot split them. To Bohr, asking what a particle is doing while nobody looks is a broken question. It is like asking what color a movie is while the projector is off. There is no picture yet. The picture happens when the light hits the screen. Before that, there is only a reel of maybes. So when you measure one particle of an entangled pair, you are part of the moment the answer forms. And because the pair acts as one connected thing, the partner far away takes on its matching trait in that same moment. No hidden slip of paper, no secret agreement made in advance. The matching is built into the deep nature of the pair, stranger than common sense allows. Most scientists found Bohr's reply convincing enough to stop worrying. They used the new physics every day. It worked. It predicted experiments perfectly. Why lose sleep over ghost stories about the moon? So the field moved on, and a quiet truce settled in. Einstein kept grumbling that reality must be solid and local. Bohr kept insisting the tiny world was as weird as it seemed. Both men grew old. Einstein died in 1955, still sure he was right. Bohr died a few years later, still sure he was right. And the deepest question in science, whether the world is truly solid and separate or strange and connected, stayed frozen, because you cannot settle a fight like this with clever words. Both men were brilliant. Both had reasons. Talking in circles could go on forever. What physics needed was a referee, some way to put the question to the universe itself and force a clear answer. Heads, Einstein. Tails, Bohr. For almost 30 years, no such referee existed. The question seemed too deep for any machine to reach. But Einstein's side still held one powerful card, an escape hatch that could make the spooky business vanish and keep the world solid and sane. People called it hidden variables, and for a long time, it was the most reasonable idea in all of physics. Imagine every particle is born with a tiny invisible instruction card tucked inside it. That is the heart of the hidden variables idea, and it is the cleverest way to rescue Einstein's view of reality. The card is too small for any machine to read, but it holds the answer to every question you might ask the particle. Measure this way, the card says heads. Measure that way, the card says tails. The answers were written at birth. If that is true, the spooky action problem melts away. Go back to the entangled coins. When two particles are born together, maybe they simply get matching cards. One card says heads, the other says tails. They carry these cards as they fly apart, across the room or across the country. When you measure your particle, you are just reading its card. When your friend measures the other, they read theirs. Of course, the answers match. They were printed together at the start. No spooky link, no faster than light whisper, no magic, just two sealed envelopes, mailed from the same place, opened far apart, boring, comforting, and completely local. Exactly the world Einstein wanted. This idea is powerful because it explains everything the strange physics explains, while keeping the floor solid under your feet. Things stay real. Things stay local. The weirdness was only an illusion, a sign our machines were too clumsy to read the tiny cards. For decades, this was a perfectly respectable belief. You could not prove it. You also could not disprove it. The hidden cards were defined as too small to ever see directly. It looked like the perfect hiding place, an idea safe from any experiment forever. And that is why most scientists thought the whole debate was pointless. If you can never test the difference, why argue? Use the math, get your answers, go home. The question of what is really happening underneath was treated like a daydream, nice to wonder about, impossible to settle. Picture two chess players frozen in the middle of a game, each certain they would win. No clock, no referee, no way to ever finish. That was physics for 30 years. Two brilliant positions, locked, with no way to play the game to the end. Almost everyone accepted that this was just how it would stay. The nature of reality was a mystery you could shrug at, but never crack. Then one man looked at the hidden cards and asked a question nobody had thought to ask. He asked a stranger question. Forget whether the cards exist. He wanted to know if they would leave a fingerprint. Would a world with secret instructions behave even a little differently from a world with spooky links? For years, he turned it over in his head as a side project, a hobby he worked on between his real job. He was not even trying to make history. He was just deeply, quietly bothered by a question everyone else had given up on. And one day, with a page of math, he found the fingerprint. He proved that a world of hidden cards and a world of spooky links would not always agree. In certain careful tests, they would give different scores, different numbers. Numbers you could actually go out and measure. The frozen game finally had a referee. The unanswerable question had become a real experiment. The man's name was John Bell, and what he found is one of the most stunning ideas in the history of human thought. John Bell grew up poor in Belfast, in Northern Ireland, the son of a family that could barely afford to keep him in school. He was a serious boy who loved books and asked too many questions. He made it to university by being relentless, and he became a skilled physicist with a steady job designing particle machines. That was his day work. Quantum weirdness was his obsession on the side. Bell was bothered by something most physicists had trained themselves to ignore. He felt the strange new physics worked beautifully but hid a deep wound at its center. The spooky action problem nagged at him. He wanted to know what was real. Late at night, on his own time, he kept circling the old fight between Einstein and Bohr. In the year 1964, while visiting America, Bell cracked it. He took the hidden cards idea seriously, more seriously than anyone before. He asked what such a world would actually look like if you ran the right test many times and kept score. Then he did the same for the spooky world the new physics described, and he compared the two scorecards. And here came the shock. They did not match. A world built on hidden cards has a hard limit. There is a ceiling on how often the entangled particles can agree, a maximum score that local, solid reality can never break. Bell worked out exactly where that ceiling sits. The spooky world has no such ceiling. The new physics predicted the particles would agree more often than any hidden card world ever could. It predicted a score that crosses the ceiling and keeps climbing. So the two views of reality finally said something different out loud. Stay under the ceiling. And Einstein was right. The world is solid cards and fair distances. Cross the ceiling, and Einstein was wrong, and the universe truly is spooky to its core. For the first time in history, the deepest question about reality had a clear test. Run the experiment, count the agreements, read the score. The universe itself would answer. This is why people call Bell's idea one of the greatest in all of science. He took a fight that seemed like pure philosophy, a thing for old men to argue over wine, and turned it into a number on a machine. And the stakes were brutal. Bell showed that one of your two precious rules had to fall. If the score crossed the ceiling, then either things have no solid traits before you look, or things can touch each other faster than light. One of those comforts had to die. The universe was going to keep one and break the other. There was no third option that kept both. That was the trap Bell sprang. Whatever the experiment showed, the world you thought you lived in was gone. Bell himself had a hunch. Quietly, he hoped the experiment would side with Einstein. He found the spooky world hard to swallow, just like his hero. He wanted the ceiling to hold. But Bell also knew something humbling. His hunch did not matter. His feelings did not matter. Only a real machine could decide. And no such machine had ever been built. And building it would be brutally hard. To read the universe's answer, you could not just measure the particles one way. You had to be sneaky about how you asked. You had to twist the question at the last second, in a way that would trap any hidden card trying to fake the result. How do you out-trick a particle that might be carrying a secret answer from birth? The method is strange and beautiful, and once you see it, you will understand exactly how three scientists finally cornered reality. Picture two detectors, one for you, one for your friend, each with a little dial on the front. The dial can point a few different ways. Before each particle arrives, you spin your dial to a random setting. Your friend, far away, spins theirs to a random setting too. Neither of you knows what the other picked. Then the particle hits, and your detector flashes one of two lights. Call them red and green. You do this over and over. Thousands of particles, thousands of random dial spins on both sides. Then you get on the phone, compare your long list of red and green flashes, and count how often you matched. That count is the whole game. Here is the clever part, the trap Bell built. The dial settings are the key. If the particles carry secret cards, those cards were printed at birth before anyone touched a dial. So a card has to guess, in advance, every possible dial position you might choose and prepare an answer for each. It is locked in early. It cannot know the spin that has not happened yet. When you run the numbers for a world like that, a hard ceiling appears. With random dials, secret cards can only make the two detectors agree up to a certain fraction of the time. Push as cleverly as you want. The cards simply cannot agree more often than that. The math forbids it. That ceiling is Bell's line. Now run the same test the way the strange physics predicts. The entangled particles, with no cards, deciding together in the moment, blow right past the ceiling. They agree more often than any secret card world could ever manage. The line breaks. So the experiment gives a single, brutal verdict. Tally the agreements. If the score sits under the line, secret cards win, and Einstein was right all along. If the score climbs over the line, cards are impossible, and the spooky world is real. There is no wiggle room. No clever card scheme can sneak above the line. Bell proved it with cold math. The ceiling is the ceiling. Think of a card cheat at a table. A cheat who knows the game in advance can rig a lot of hands. But even the best cheat, locked into a plan before the dealing starts, can only win so often when the rules keep changing at random. Cross that win rate again and again, and you are no longer looking at a cheat with a hidden plan. You are looking at something that bends the rules of the table itself. That is what crossing Bell's line would mean. A universe that bends the rules of space and cause. The beauty of it is that you do not need to believe anyone. You do not need to trust Einstein or Bohr. You just run the machine and read the number. Reality grades its own test. Bell handed the world this gift in 1964. A clean way to settle the deepest question there is. And then, the strangest thing happened. Almost nobody picked it up. For years, his brilliant test sat on a dusty shelf, ignored by nearly the entire field, while the answer to reality itself waited, untouched, for someone to care. In the 1960s, asking what is really real could end your career before it started. Physics was booming, and the money was in things you could build. Lasers, transistors, bigger atom smashes. Young scientists were told to shut up and calculate, to use the strange physics like a tool and stop asking what it meant underneath. The deep questions had a bad reputation. They were seen as soft, fuzzy, almost embarrassing, the work of dreamers, not real scientists. So Bell's beautiful test landed in a desert. He had published it in a small, obscure journal that folded soon after. Hardly anyone saw it. Of those who did, most shrugged. They figured the answer was already known. Bohr had won the old argument decades ago, hadn't he? Why waste a good machine proving the obvious? There was also a colder reason. Testing Bell's idea was a great way to ruin yourself. Imagine telling your boss you wanted to spend years and real money to check whether reality is real. You would sound like a crank. No respectable lab wanted to fund a question that smelled like philosophy. Careers were built on safe, useful work, and this was the opposite of safe. So for almost 10 years, the loaded gun Bell had built just sat there. The single most important question in science had a clear path to an answer, and the field walked right past it, eyes forward, too busy and too cautious to look. Think of a treasure map left on a library shelf, with the gold sitting exactly where the X says. People stroll by the shelf every day. Nobody pulls the map down. Not because it is fake, because digging looks foolish, and everyone has a job to do. Bell himself watched this silence with a kind of patient sadness. He kept his day job building particle machines. He believed his test mattered deeply, but he could not force anyone to run it. He could only wait and hope that someone, somewhere, was stubborn enough to ignore the warnings. And someone was. Out in California, a young physicist was reading Bell's forgotten paper and feeling his pulse quicken. He was a bit of a troublemaker, the kind of person who enjoyed poking at things he was told to leave alone. The deep questions did not embarrass him. They thrilled him. But the twist makes his story sting. He wanted Einstein to win. He picked up Bell's test as a weapon to tear the spooky physics apart. He believed, deep in his gut, that Einstein was correct. He thought reality had to be solid and local, and he wanted to be the one to prove it. He pictured himself running the experiment, watching the score stay safely under the line, and showing the world that the spooky stuff was a mistake. He was about to spend years of his life, and a lot of borrowed equipment, chasing that dream, and the universe was about to break his heart. His name was John Clauser, and to even get started, he had to walk into the office of the most famous physicist in America and survive being laughed out of the room. John Clauser was the kind of student who argued with his professors and usually thought he was right. He had grown up around science. His father was an aircraft engineer, and young Clauser loved taking machines apart to see what made them tick. He was smart, restless, and allergic to being told what to believe. When teachers said the spooky physics was settled, that Bohr had won and the matter was closed, something in Clauser pushed back. How could it be settled if nobody had ever tested it? Then he found Bell's forgotten paper, and it lit a fire in him. Here was a real test, a way to stop arguing and start measuring. Clauser read it again and again, and the more he read, the more he believed he could win. Because Clauser, like his hero Einstein, was sure the world was solid and local. He felt it in his bones. He wanted to run Bell's test, watch the score stay under the line, and prove the whole spooky business was a fairy tale. There was just one problem. Bell's original idea was a thought experiment. It described a perfect, clean test that no real machine could quite pull off. Real detectors are clumsy. Real particles leak and scatter. To actually build this thing, someone had to rewrite Bell's idea into a form a real lab could handle. Clauser was not the only one thinking this way. A teacher named Abner Shimony and his student Michael Horn had been chewing on the same problem on the other side of the country. So had a young researcher named Richard Holt. When they all realized they were after the same prize, they joined forces. Together, the group reshaped Bell's pure idea into a tougher, real-world version. A recipe a working lab could actually follow. It told you exactly what to measure, how to set the dials, and where the ceiling would sit. They had turned a dream into a blueprint. Now Clauser just needed two things: a real laboratory, and permission from people who thought his whole quest was a waste of time. That second part was the killer. Picture being young and unknown, walking into a room full of legends and announcing that you want to test whether reality is real. These were people who had helped build the strange physics. To them, the question felt childish, or worse, insulting. They had moved on decades ago. Why was this kid dragging them back? Clauser felt the cold stares. He heard the polite versions of, "Are you serious?" Most senior scientists told him, in one way or another, to drop it and do real work. The experiment was hard, expensive, and pointless, they said, because everyone already knew the answer. But Clauser had a stubborn streak a mile wide. The colder the room got, the more he wanted to do it. He kept knocking on doors, hunting for a lab that would let him try, hunting for anyone who would not laugh. So he went to ask one of the most brilliant physicists alive for advice. A living legend, famous for his wild mind and his sharp tongue. It was one of the worst meetings of Clauser's young life. The legend listened for a moment, then threw him out of the office. The famous physicist was named Richard Feynman, and almost everyone treated him like a god. Feynman was a superstar of science, known for explaining hard ideas with joy and for cutting down sloppy thinking in seconds. If you wanted to know whether your physics idea was any good, he was the man to ask. He was also blunt to the point of cruelty. Clauser came to him excited, ready to explain his plan to test the deepest question in physics. He wanted Feynman's blessing, or at least his interest. He got neither. The way Clauser later told it, Feynman barely let him finish. The great man waved the whole idea away. To Feynman, testing the strange physics was a foolish errand. The theory worked. It had passed every other test for decades. Why on earth would you spend years checking something so obviously true? He told Clauser, in so many words, to come back only after he had found an actual error in the theory. Then he showed him the door. It stung. Imagine pouring your heart into an idea, finally getting a moment with your hero, and watching him swat it down like a fly. A lot of young scientists would have quit right there. The message could not have been clearer. Smart people did not waste time on this. The door, literally, was closed. But Clauser was wired differently. Getting thrown out did not crush him. It made him angry, and the anger made him more determined. If the legends were this sure, this dismissive, then maybe they had stopped questioning. Maybe they were defending a belief they had never actually checked. That thought only sharpened his hunger to run the test himself. He found his chance at the University of California in Berkeley. He landed a job there, and he met a graduate student named Stuart Friedman who was willing to take the risk with him. Two young men, one wild idea, and a lot of doubters watching to see them fail. They were given a room nobody wanted, a space in the sub-basement of an old physics building, down where the pipes hummed and the daylight never reached. It was cramped and unglamorous. It was perfect, out of sight, away from the people who thought they were wasting everyone's time. And then came the hard part, building a machine delicate enough to ask the universe its deepest question. This was not like ordering a part from a catalogue. Clauser and Friedman had to build much of it by hand. They needed to create entangled particles of light, send them flying in opposite directions, and catch them in detectors sensitive enough to read single flickers of light. Every piece had to be tuned with insane care. A speck of dust, a wrong angle, a flickering bulb, any of it could ruin the whole reading. For months, they fought the machine. They coaxed it, fixed it, cursed it, and tuned it again. Clauser, the man who wanted to prove Einstein right, was pouring his life into a contraption that would finally settle the score. He was so close now. Soon the machine would run, the lights would flash, and the universe would hand over its answer. He was certain that answer would crown Einstein the winner. He could not have been more wrong. In the year 1972, deep in that basement, the machine finally came alive. At the heart of it sat a glass tube full of calcium, the same silvery metal found in chalk and in your bones. Clauser and Friedman heated the calcium until it glowed. When you excite a calcium atom just right, it spits out two tiny flashes of light in a single breath, one after the other, and those two flashes come out entangled, born together, linked. This was their source of magic coins. A steady drip of paired light particles, sprayed out in opposite directions, ready to be questioned. On each side of the tube, about 10 feet apart, stood a detector with a special filter, the dial from Bell's test made real. The filter could be set at different angles. Each angle was like asking the light particle a slightly different question: pass through or get blocked, red light or green light, yes or no. The plan was simple to say and brutal to do. Fire out millions of entangled pairs. For each pair, record whether both sides agreed, set the filters at different angles, and keep a careful tally. Then compare the total against Bell's ceiling, the line that separated Einstein's world from the spooky one. The trouble was, the signal was painfully faint. We are talking about catching single specks of light, the dimmest flickers imaginable, against a world full of noise. Stray light, electrical hiccups, the hum of the building, all of it threatened to drown the answer. To gather enough clean flashes, the experiment had to run for a long, long time. Days bled into weeks. The machine purred and clicked in the dark, while Clauser and Friedman watched the counts slowly pile up. It happened slowly and quietly, just numbers crawling higher, one detection at a time, building toward a verdict. Picture two people panning for gold in a freezing river, swirling pan after pan of mud, hour after hour, waiting for the tiny gleam that tells them the work was worth it. That was the rhythm of it. Patience, cold metal, and a question hanging in the air. And the whole time, Clauser was rooting for a particular answer. He wanted the final score to land under Bell's line. He wanted to see the entangled particles behave like ordinary coins with secret cards inside, agreeing only as often as solid, local reality allowed. He wanted to walk upstairs and tell the doubters that Einstein had been right, and that the spooky stuff was just a story we told ourselves. Every new batch of data brought him closer to knowing. The tension must have been unbearable. Years of work, a hostile field, a hero to defend, all of it riding on a column of numbers ticking upward in a basement. Finally, they had enough. Enough flashes, enough pairs, enough clean data to trust the result. They added it all up and compared the score to Bell's ceiling. The number was in, and it sat well above the line. The entangled particles had agreed more often than any world of secret cards could ever allow. The ceiling that protected Einstein's solid, local reality had shattered. Clauser stared at the result that destroyed his own dream. He had built the perfect machine to crown his hero, and his machine had just told him, without mercy, that his hero was wrong. John Clauser had set out to prove Einstein right, and instead he became the first person to prove him wrong. Sit with how strange that is. The experiment was his idea. He built the machine with his own hands. He wanted, more than anything, for the spooky physics to fail, and the universe looked him in the eye and told him no. The strange answer was the true one. Years later, Clauser admitted how it felt. He said he had been stunned, even a little heartbroken. He repeated the test, checked it, ran more versions of it, hunting for a mistake that would save Einstein. Every time, the same answer came back. The particles broke the ceiling. Bohr was right. Einstein was wrong. So what had he actually shown? Remember the trap Bell built. If the score crossed the line, one of your two comforting rules had to fall. Either things have no solid traits before you measure them, or things can reach across space faster than light. The basement experiment said the world really does work that way. One of those rules was broken. For good. This was earth-shaking. A young man in a basement had reached out and touched the deepest question humans had ever asked. The question of what is real, and gotten a clear answer from nature herself. The smartest scientist who ever lived had guessed wrong about the bones of reality. You might expect parades, headlines, a shocked world. Instead, the reaction was a quiet murmur. A handful of physicists noticed. Most of the field kept doing what it was doing. The result was too strange, too far outside normal work for people to fully absorb. It would take decades and a string of even better experiments before the world truly understood what had happened in that sub-basement. And there was a real reason for the caution. As strong as Clauser's result was, it had cracks, tiny gaps in the experiment where a clever defender of Einstein could still wriggle through. His detectors, for example, were far from perfect. They missed a lot of the light particles, catching only a small share of them. So a stubborn skeptic could argue something sneaky. What if the particles you happened to catch were a biased sample? What if the ones that slipped away would have told a different story, one that kept the ceiling safe? It sounds like a stretch, but in science, a stretch is enough to keep a question open. If there is any door, however narrow, that lets the old reality survive, you have to close it before you can truly declare the case won. Clauser had blown a hole in Einstein's world, but he had not sealed every escape route. A few loopholes remained, thin and unlikely, yet alive, and as long as they stayed open, a determined believer could still whisper that maybe, just maybe, the world was solid and local after all. To truly corner reality, those loopholes had to die, one by one. Closing them would take new minds, sharper tools, and tricks that sound almost impossible. Scientists would end up switching their detectors faster than light could travel, and even letting ancient starlight make their choices for them. The hunt to trap the universe was just beginning, and the next loophole was the trickiest of all. To kill Einstein's world completely, scientists had to slam shut 3 secret doors. 3 ways reality might still be tricking them. Think of it like proving someone cheated at cards. Catching them once is not enough if they can say the deck was marked, or they got lucky, or someone signaled them. You have to rule out every excuse. Quantum physics faced the same problem. Each loophole was an excuse the universe might be using to fake the spooky result. The first door was the one that cracked Clauser's experiment. Call it the missed particle problem. His detectors only caught a small slice of the light particles flying out. A skeptic could argue that the captured few were a lucky sample, and that the millions that slipped past would have behaved like good, solid, local particles. Close this door, and you prove the result is real and not just a trick of weak detectors. The second door was about timing and whispering. In the basement experiment, the 2 detectors sat only 10 feet apart, and their dial settings were chosen well before the particles arrived. That left a frightening possibility. What if one particle somehow sent a secret message to the other, a hidden whisper traveling at or below light speed, telling its partner how to answer? 10 feet is nothing. Light crosses it in a flash. If there was time for a signal to sneak across, the matching might be an ordinary trick after all. To slam this door, you would have to choose your dial settings at the very last instant, after the particles were already in flight, and place the detectors so far apart that no whisper, even one moving at light speed, could possibly cross in time. You would have to outrun light itself. The third door was the strangest, and it crawled under your skin the more you thought about it. Call it the rigged choice problem. The whole test depends on the dial settings being truly random and free. But what if they were steered? What if some hidden thread, running through all of history, secretly linked the particles and the choices of the people measuring them? Then the universe could be quietly coordinating everything in advance, faking the spooky result through a grand, invisible setup. That third door sounds like paranoia. It nearly is. But it was a real gap, and a careful scientist could not simply ignore it. So there they were. 3 doors. The mist particles, the secret whisper, the rigged choice. As long as even one stayed open, a clever defender of Einstein could keep the dream of a solid, local world alive. The next 20 years became a hunt to close all 3. It pulled in new scientists, faster electronics, longer distances, and ideas so bold they sound like science fiction. Each experiment was harder than the last. Each one sealed another escape route. Each one pushed reality further into the corner. And leading the charge against the second door, the secret whisper, was a quiet, patient French physicist who had read Bell's work as a student and never let it go. He decided to do something that sounded impossible. He would change the questions faster than light could carry the answer. He would force the particles to commit before any signal could pass between them. No time to whisper, no time to cheat. If the matching still held under those rules, the secret whisper excuse was finished forever. His name was Alain Aspect, and his experiment would become one of the most beautiful in the history of physics. Alain Aspect first read Bell's paper as a young man, and it changed the course of his life. He was working as a teacher in a hot, faraway country when he came across the idea. The moment he understood it, he knew what he wanted to do with his career. He would build the experiment that closed the secret whisper door. When he brought the plan to Bell himself, the older man asked if Aspect had a permanent job, worried that chasing such a wild question could wreck a young scientist. Aspect did have the job, so he dove in. The whisper problem came down to speed. In the basement test, the dials were set early, giving any hidden signal plenty of time to sneak between the detectors. Aspect's fix was bold. He decided to change the dial settings while the particles were already racing through the air, switching the question at the last possible heartbeat. Picture 2 people taking a test in separate rooms, far apart. Normally, they get the questions in advance. There is time to pass a note under the table. Aspect slammed that window shut. He waited until each person had already started writing, then swapped their questions at the final instant, far too fast for any note to travel between the rooms. To pull this off, he built a device that could flip the setting of each detector in a matter of billionths of a second. The 2 detectors stood about 40 feet apart. Now, light is fast, but even light needs time to cross 40 feet. Aspect made his switches happen faster than that crossing time. So when one detector chose its question, the other particle could not possibly have heard about it. No whisper could move quickly enough. He had outrun light. Then he ran the test, over and over, switching the questions in flight, catching the flashes, and tallying the score. The particles did not care. They kept right on breaking Bell's ceiling, agreeing far more often than any solid local world could allow. Even with no time to send a secret signal, even with the questions changing at the last instant, the matching held perfectly. The whisper door slammed shut. There was no hidden message passing between the particles because there was simply no time for one to travel. And yet they still answered as one. Whatever links entangled particles moves faster than light, and it behaves like something far deeper than any signal crossing through space. This was the result that really woke the world up. Aspect's experiment, done in the early 1980s, was so clean and so clever that physicists could no longer look away. The spooky world was real, and now it had survived a far tougher test than Clauser's. 2 of the 3 doors were badly damaged. The mist particles door and the secret whisper door were both crumbling. 1 door remained, the strangest one, the rigged choice. And to close it, scientists would attempt something that sounds completely insane. They would take the choice out of human hands entirely and hand it to the stars. They would let light that left distant suns long before you were born decide how to set the detectors. Light so old and from so far away that nothing on Earth could have secretly arranged the result in advance. To beat the last loophole, they were going to reach across the sky and across time itself. Here is a thought that has kept some physicists awake at night. What if you were never truly free to choose? The last loophole rests on one quiet assumption buried inside every version of the test. When a scientist spins a dial to pick a setting, we assume that choice is free and random. We assume nothing reached back in time to nudge it. That feels obvious. You decide, in the moment, where to point the dial. Who could argue with that? But imagine a universe with a hidden thread running through everything, a thread stretching all the way back to the beginning of time. Suppose that thread secretly connects 2 things that should have nothing to do with each other: the particles in the experiment and the so-called free choices of the people measuring them. If such a thread existed, the whole result could be a setup. The particles could carry secret cards after all, printed at birth, and the universe could quietly arrange for every scientist to pick exactly the dial settings that make those cards look spooky. The choices would feel free. They would look random, but they would have been steered all along by a plan written into the world from the very start. In that strange picture, Einstein could still be right. Reality could still be solid and local. The spooky matching would be a grand illusion, stage managed by a cosmic script that decided everything in advance, including your decisions. Most scientists find this idea deeply unpleasant. If your choices are secretly rigged, then no experiment means anything, ever. Science itself stops working because you can never trust that you freely set up your own test. It is the kind of loophole that, if true, breaks far more than quantum physics. It breaks the whole idea of asking nature honest questions. Still, you cannot close a door just because you dislike what is behind it. The rigged choice loophole was real, and a careful scientist had to take it seriously, no matter how much it itched. So, how do you prove your choices were free? How do you show that nothing reached forward from the dawn of time to fix the settings of your machine? You cannot read the mind of the universe. You cannot prove your own thoughts are unscripted. The problem seems hopeless. For a while, it looked like this door might never close, a permanent crack of doubt in the proof that reality is strange. Then a few bold scientists had a wild idea. If you cannot trust a human to make a free choice, and you cannot trust a machine on Earth, then reach for something no earthly plot could have touched. Reach for the oldest, most distant light there is, the light of the stars. A star far across the galaxy sent its light toward Earth long before the experiment, before the lab, before you were even born. If you let that ancient starlight set your dials, then any secret plan to rig the choice would have to have been laid unimaginably long ago, across an unimaginable distance. And the boldest version of this plan would not stop at nearby stars. It would reach for objects so far away that their light has traveled for billions of years, almost from the dawn of the universe itself. They were about to put the entire cosmos on the witness stand, and what the starlight revealed would push the strangeness further than anyone dared to hope. In the year 2017, a team in Austria pointed 2 telescopes at 2 different stars and let the starlight run their experiment for them. The idea was beautiful in its boldness. To close the rigged choice door, they needed the dial settings to come from somewhere no earthly plot could have reached. So they handed the job to light that had been traveling toward Earth for centuries. from stars hundreds of years away. Here is how it worked. Each telescope stared at its own star and watched the color of its light. Starlight flickers, and its exact shade arrives as a kind of natural coin flip, decided long ago at the surface of a distant sun. The team used that color in the instant it arrived to set their detector, a redder flicker, one setting, a bluer flicker, the other. The star chose the question. Think about what that means. The light hitting one telescope left its star around the time of the American Revolution. The light hitting the other left its star centuries before that. For any hidden plan to rig these settings, the plot would have to have been set in motion hundreds of years ago in two different stars, light years apart, with no way to know they would ever be used in a lab in Austria. The two telescopes sat about 1.25 miles apart. Between them, the entangled particles flew to their detectors, and the ancient starlight told each detector how to ask its question at the last possible instant. Then the team counted the matches. The particles broke Bell's ceiling again. Even with stars setting the dials, even with choices made by light older than any country on Earth, the spooky matching held strong. The score climbed over the line, exactly as the strange physics predicted. Picture a courtroom where you suspect the jury was bribed, so you replace them with people chosen at random from two distant towns, picked by events from long before the crime happened. Now no briber could have reached them in time. If the verdict still comes back the same, you can finally trust it. The starlight was that untouchable jury. This pushed the rigged choice door almost shut. To still save Einstein's world, a believer would now have to claim that some plan, written hundreds of years ago in the hearts of separate stars, had secretly arranged everything. The idea was straining to the breaking point. But the team behind this test was not satisfied with hundreds of years. A few centuries of cosmic head start still left a sliver of room for doubt. A truly stubborn skeptic could imagine a plot stretching back even further. So the scientists asked a daring question. How far back could they push the choice? Could they let the dials be set by light that left its source not hundreds of years ago, but billions? Light so old it carried us most of the way back to the birth of the universe itself. To do that, they would need the brightest, most distant beacons in all of creation. Objects that shine across nearly the entire history of time. And those beacons exist. They blaze at the edge of the visible universe, swallowing whole stars to fuel their light. The scientists were about to aim their telescopes at the most violent objects ever found and let them be the judge. At the far edges of the universe burn objects so bright they outshine entire galaxies, powered by giant black holes tearing stars apart. We call them quasars. A quasar is the blazing core of a young galaxy where a monster black hole is feeding. As gas and stars spiral into it, they heat up and scream out light, the brightest steady glow in all of creation. Quasars are so far away that their light has been traveling toward us for billions of years. When you look at one, you are seeing the universe as it was when it was young. In the year 2018, on the Canary Islands off the coast of Africa, scientists aimed their telescopes at two of these ancient beacons. They used the same trick as before, but turned all the way up. The flickering light of each quasar, born billions of years ago, set the dials of their detectors. Let that distance sink in. The light from one quasar left its source around 8 billion years ago, long before the Sun and the Earth even formed. The other was just as ancient. For any hidden plan to have rigged these settings, the scheme would have to reach back across most of the lifetime of the universe, threading together objects on opposite sides of the visible cosmos that have never been in contact. That is the kind of plot nobody can take seriously. It would mean the entire universe, from near its birth, had conspired across billions of years just to fool a handful of scientists on a small island. At that point, the rigged choice idea collapses under its own weight. And once again, the particles broke Bell's ceiling. Quasars at the edge of time set the questions, and the entangled flashes still answered as one, more often than any solid, local world could allow. The spooky matching survived even this. Picture trying to fix a coin flip. First you suspect the flipper, so you replace him. Then you suspect the coin, so you swap it. Finally, in desperation, you let the flip be decided by an event from the dawn of history, on the far side of the world, that no living person could have arranged. If the result still comes out the same, the game is honest. There is no one left to blame. The quasar test was that final, impossible coin flip. The universe itself, reaching back nearly to its beginning, served as the judge, and the verdict stood. The rigged choice door was now pressed shut so tightly that almost no serious scientist worried about it anymore. The strange physics had survived a challenge written across the entire sky and nearly the whole age of time. 2 of the 3 doors were now sealed by these heroic tests. The secret whisper, closed by aspect. The rigged choice, closed by the stars and the quasars. 1 door remained, the very first one, the mist particle problem that had nagged at Clauser's basement result from the start. To truly trap reality, every door had to shut at once, in a single experiment, with no excuse left standing. And in the year 2015, in a quiet lab in the Netherlands, a team finally pulled it off. The last escape route was about to vanish. In the year 2015, scientists in the Netherlands ran the experiment that left reality with nowhere to hide. The problem before had always been that you could close 1 door, but another would creep open. Clauser's mist particles, the secret whisper, the rigged choice. Each great experiment slammed 1 door, yet a clever skeptic could point to a different one and say, but what about that gap? To truly win, someone had to shut every door in a single test, all at once. A team in the Dutch city of Delft found a way. Instead of using flickering light particles, which are easy to lose, they used something they could hold on to. They trapped single electrons inside tiny flaws in diamonds. An electron caught this way stays put. You can question it again and again without it slipping away. That solved the mist particle problem. Nothing escaped uncounted. Then they placed their 2 diamonds far apart, on opposite sides of a college campus, about a mile apart. That distance was the key to the secret whisper door. With the detectors that far apart and the questions chosen at the last instant, no signal, even one moving at light speed, could cross between them in time. There was no chance for one particle to tip off the other. So, in one careful experiment, 2 of the deadliest doors closed together. No lost particles, no time to whisper, and the team took fierce care to keep their choices random and clean, guarding against the rigged choice problem too. It was brutally hard. To entangle 2 electrons sitting a mile apart, the team had to perform a delicate trick, linking them through flashes of light sent to a meeting point between them. Most attempts failed. The successful events were painfully rare, sometimes only a handful in a whole day. They had to run the experiment for weeks, gathering each precious matched pair like drops of rain in a cup. And when they finally had enough, the answer was the same one Clauser had found in his basement more than 40 years before. The particles broke Bell's ceiling. They agreed more often than any solid local world could ever permit. This time, with every door shut at once. Picture a detective who has finally ruled out every alibi. The suspect cannot claim the witnesses were unreliable because they all spoke, cannot claim a secret message passed because there was no time, cannot claim the jury was rigged because the choices were sealed and random. Every excuse is gone. The verdict is simply true. That was the moment. Other teams, working with light particles, reached the same airtight result that same year. Reality had been cornered from every side, and it gave the same answer every time. Einstein's solid, local world was finished. The spooky world was real, proven beyond any reasonable escape. This string of experiments, from Clauser's basement to Aspect's flying questions to these final loophole-free tests, is exactly what the Nobel Committee honored years later. The work had taken half a century and the lives of dozens of scientists, and it ended in a single, stunning fact about the universe you live in. But proving that the spooky link is real is only half the story. The deeper shock is what people learn to do with it. Because once you can entangle particles on demand, you can start doing things that sound like pure science fiction, starting with teleportation. The word teleportation makes you think of a person stepping into a booth and reappearing across the galaxy. The real thing is stranger, and scientists have actually done it. Here is the puzzle it solves. Every particle carries a state, a complete set of traits that says exactly what it is doing. Its state is its identity. Now, suppose you want to copy that state perfectly onto another particle far away. In the quantum world, this is supposed to be forbidden. The moment you measure a particle to learn its state, you disturb it and scramble the very thing you were trying to copy. You destroy the secret by looking at it. So how do you move a particle's exact state across a room without ever reading it? The answer is entanglement. In the year 1997, Anton Zeilinger and his team pulled it off. Zeilinger was the third of our 3 Nobel winners, an Austrian physicist with a gift for turning wild ideas into real machines. He and his group teleported the state of one particle of light onto another. The trick works like a relay. First, you make a fresh, entangled pair, and you send one of them to the faraway spot. Now you have a spooky link stretched across the gap. Then you take your mystery particle, the one whose state you want to move, and you let it interact with your end of the entangled pair. You make a careful joint measurement of the two together. Something remarkable happens. That measurement instantly imprints the mystery state onto the faraway particle through the entangled link without anyone ever reading the state directly. The faraway particle becomes a perfect copy of the original, and the original is wiped clean in the process, its state gone, transferred away. Picture a sealed letter you need to deliver, but the ink vanishes the instant anyone opens the envelope. You cannot read it and recopy it. So instead, you use a strange pair of magic envelopes that share a hidden link. By combining your sealed letter with one magic envelope and reporting what you see, the exact words appear inside the other magic envelope, miles away, while your original page goes blank. The message moved without ever being read. That is quantum teleportation. The particle itself does not travel, its identity does. The state leaps from here to there, carried by the spooky connection, and the original is erased so that no copy is ever left behind. This was a jaw-dropping demonstration. It proved that entanglement is more than a curiosity. It is a tool. You can use the spooky link to move quantum information from place to place, perfectly, in a way ordinary physics forbids. And teleportation is the seed of something huge. It is one of the basic moves inside future quantum machines and quantum networks. To send fragile quantum information across a city or a country, you may one day rely on exactly this trick, repeated again and again down a chain. But Zeilinger was not done shocking people. He took entanglement one step further, into territory that sounds flatly impossible. He found a way to link two particles that had never met, never touched, and never shared any past at all. Two total strangers, bound together by a spooky thread out of thin air. Two particles are born on opposite sides of a room with no connection between them. They have never touched. They have never been near each other, and scientists can still force them to become entangled. This is called entanglement swapping, and Zeilinger's team made it real in the year 1998. It pushes the spooky link into a place that feels like it should be off limits. Walk through how strange it is. Start with two separate entangled pairs. Call them pair 1 and pair 2. In pair 1, particle A is linked to particle B. In pair 2, particle C is linked to particle D. A is linked to B. C is linked to D. And the two pairs have nothing to do with each other. A and D have never met. They were born in different places, from different sources. Now bring the two inside particles, B and C, together at a meeting point. Make a special joint measurement on them. And in that instant, something incredible happens to the two outside particles, A and D. They become entangled. The strangers are now linked. Measure A and D answers in perfect step, even though they share no history at all. The link did not pass through space in the normal way. It was forged by measuring their partners. The spooky connection jumped across, swapping from the original pairs onto two particles that had never interacted. Picture two pairs of best friends who have never met the other pair. You take one friend from each pair and have them shake hands in a back room. Somehow, that single handshake makes the two friends who stayed behind, who have never seen each other, finish each other's sentences for the rest of their lives. A bond appears between two strangers, created entirely through their partners. This sounds like a party trick, but it is one of the most important tools in all of quantum science. Here is why it matters so much. The spooky link is fragile, and it fades over long distances. If you try to send entangled light through miles of cable, it gets lost and scrambled. So how could you ever connect particles across a whole country? Entanglement swapping is the answer. You make many short links, then stitch them together, swapping the entanglement down the line, hop by hop, until two particles at opposite ends of a long chain are joined, even though they began as strangers. This is the backbone of the dreamed-of quantum internet, a future network where distant cities are linked by entanglement, allowing perfectly secure messages and connected quantum computers. Every long stretch of that network would be built from this exact trick, joining strangers through their partners, again and again. So, entanglement is not only real, it is something you can build with, stretch, and pass along like a baton. By now, you might be feeling a wild temptation. If two particles answer each other instantly, across any distance, then surely we can use this to send messages faster than light. A galactic telephone, instant communication across the stars. It seems like it must be possible. It is one of the most natural conclusions you could reach, and the universe shuts it down completely, in a way that is almost cruel. Here is the heartbreak at the center of entanglement. The spooky link is instant. It spans any distance, and you can never use it to send a single message. It feels like it should be the ultimate phone. Two entangled particles answer each other in the same instant, no matter how far apart. Put one on Earth and one on a starship at the edge of the galaxy, and the matching still holds with zero delay. Surely you could tap out a message, light years away, faster than any radio wave, a way to beat the cosmic speed limit at last. The universe says no, and the reason is buried in a single word: random. Remember what each particle does on its own. When you measure your half of an entangled pair, your result is pure chance, heads or tails, with no pattern you can control. You cannot force your particle to land heads. You cannot make it spell out a letter or a number. You just get whatever random answer comes up. So picture you and a friend light years apart, each holding one particle of a pair. You measure yours and get a random string of heads and tails. Your friend measures theirs and gets a random string too. Later, when you compare, you find the two strings match in their spooky way. But while it was happening, neither of you saw anything but noise. Random flips. There was no message in it, because you could not steer your own results. To send a real message, you need control. You need to choose what the other person sees, and entanglement gives you no control at all. Your end is a coin you cannot load, so you can never push information across the link. The matching only reveals itself later, when the two random lists are brought together and compared, and that comparison has to travel the old-fashioned way, no faster than light. Think of two people in distant cities, each opening a long row of envelopes filled with random numbers. The numbers in their two stacks magically agree, envelope by envelope, but neither person chose those numbers. Neither can slip a secret note inside. They only discover the strange agreement afterward, by mailing their lists to each other through the normal post. The spooky match is real, yet it carries no message, because nobody got to write it. That is the universe's strange compromise. It allows the instant connection, the deep weirdness that broke Einstein's world. And in the same breath, it protects the speed limit of light by making sure that connection can never carry a usable signal. The two great rules end up in an uneasy truce. Reality is spooky, and yet you still cannot send a faster-than-light text. It is a stunning piece of cosmic fine print. The link is more intimate than anything in classical physics, and also perfectly useless as a telephone. So, entanglement is real, deep, and strangely sealed off from sending messages. By now, you might think this weirdness only lives in the world of single particles, things far too small to ever see. But the strangeness does not stop at the tiniest scale. Scientists have caught much bigger things behaving in this blurry, quantum way, things made of dozens of atoms, acting like ghosts. We tell ourselves that quantum weirdness only happens to things too small to see. Scientists keep proving that comfort wrong. Deep down, every particle has a split personality. It can act like a tiny solid ball, and it can act like a spread-out wave, blurry and smeared across space. A single particle of light can pass through two openings at once, like a wave rippling through both, then land as a single dot, like a ball. This blurry double life is the heart of quantum strangeness. While nothing watches, the particle is a foggy wave of maybes. When you measure, it snaps into one solid spot. For a long time, people hoped this only happened to the very smallest things. A lone particle of light, a single electron, something so tiny it lives in a different world from chairs and people. That hope made the weirdness easier to swallow. Out there, in the realm of the unimaginably small, fine, let it be strange. In here, with real objects, things stay solid. Then Zeilinger's team, among others, started pushing the size limit. They asked a daring question: how big can an object be and still act like a blurry wave? They reached for a molecule called a buckyball. It is a tiny cage of carbon, built from 60 carbon atoms, shaped almost exactly like a miniature soccer ball. By the standards of the quantum world, a buckyball is a giant. It is far bigger and heavier than a single particle of light. It is a real, complex object, the kind of thing you might expect to behave like an ordinary speck of dust. They fired these buckyballs, one at a time, at a barrier with narrow openings, and watched where they landed. If a buckyball were just a tiny ball, each one would go through one opening and pile up in a simple pattern. But that is not what happened. The buckyballs behaved like waves. Each single molecule seemed to pass through more than one opening at once, spreading out, then landing in a striped pattern that only waves can make. A soccer ball of 60 atoms was living the same blurry double life as a lone particle of light. While unwatched, it was a smeared wave. When measured, a solid dot. Picture rolling a real soccer ball toward a wall with two doorways, and somehow the ball goes through both doorways at the same time, then arrives as one ball on the far side. With a real soccer ball, that is madness. With a buckyball, it is exactly what the experiment shows. This was a thunderclap. The quantum fog was not trapped in the world of single particles after all. It reached up to objects made of dozens of atoms, things on the edge of what we might one day almost see, and scientists have since pushed even further, coaxing larger molecules into the same ghostly behavior. So where does it stop? Why do you and your chair and the moon look so solid when the pieces you are built from are blurry waves of maybes? That question is still open, and it is one of the deepest mysteries left in all of physics. We have followed the spooky link from a basement, across the sky, into teleportation, and up to molecules acting like ghosts. Now it is time to say plainly, in simple words, what all of it actually means. The verdict on reality itself. After 50 years of experiments, here is the plain verdict. The universe is not locally real, and those few words rewrite what you are. Take them one at a time, because each one breaks a rule you have trusted your whole life. Start with real. Real means a thing has its traits. Whether or not anyone looks, The experiments say no. A particle does not carry a fixed answer before it is measured. It sits in a fog of maybes, holding many possibilities at once, and only commits to one when something checks. The trait is not waiting inside, hidden. It forms in the moment of measuring. Before that, in a deep sense, it simply is not there yet. Now take local. Local means nothing can affect a faraway thing faster than light. The experiments say no to this too. Entangled particles answer each other in the same instant, across any distance, with a connection that no signal could carry in time. Their bond does not travel through the space between them. It acts as if that space barely matters. Put the two together. The world is not locally real. Things have no fixed traits until measured, and deeply separated things are linked in ways that ignore distance. Both of Einstein's comforting rules, the solid floor everyone stands on, turned out to be false at the bottom of nature. This is the discovery the three scientists were honored for. Clauser lit the spark in his basement. Aspect outran light with his flying questions. Zeilinger sealed the case and turned the weirdness into tools. Together, their work forced the world to accept a reality stranger than the smartest human had been willing to believe. And here is why it should give you chills. You are not separate from this. You are made of the very particles that play by these rules. Every atom in your hand, every speck of you, is built from pieces that hold no fixed traits until measured, pieces that can link across space in spooky ways. The strangeness is not far away in a lab. It is the fabric you are sewn from. Picture believing your whole life that the ground is solid stone, only to learn that, looked at closely enough, it is shifting fog that hardens into stone the instant you step on it. You never noticed, because it always firms up exactly when you check. That is the world the experiments reveal. Solid when measured, foggy and undecided when not. So why does life feel so normal? Why does your chair stay a chair, and the moon stay in the sky? That is one of the great open puzzles. Somehow, when countless particles gather into big, everyday objects, the fog settles into the steady, solid world you know. The blurry maybes of the tiny scale wash out, and you are left with reliable stuff you can sit on and lean against. Scientists are still working out exactly how that smoothing happens. But accepting that the world is not locally real opens a door to a question even deeper and more unsettling. The experiments all hinge on one word that we have used again and again without ever pinning it down. Measuring, looking, checking. What does that even mean? What counts as a measurement powerful enough to freeze the fog into a fact? Nobody fully knows. And the mystery hiding inside that simple word may be the strangest part of all. Every experiment in this story depends on one magic moment. The moment of measurement, when the fog of maybes snaps into a single fact, and nobody can say exactly what that moment is. It sounds like it should be simple. You measure a particle. The blur becomes a result. But push on the word measure, and the whole thing turns slippery. What actually counts as a measurement? What has the power to freeze a wave of possibilities into one solid answer? Is it when the particle hits a detector? When a needle moves? When a number lights up on a screen? When a scientist glances at that number? When the scientist's brain understands it? Each of those is just more particles bumping into other particles. If a lone particle can sit in a fog of maybes, then so can a detector, and a needle, and a screen, all of which are made of particles too. So where, in that chain, does the fog finally collapse into a fact? This is one of the deepest unsolved riddles in all of physics, and it has a name: the measurement problem. The strange physics is brilliant at predicting what answers you will get. It is silent on why or when the maybes turn into one real result. The theory tells you the odds perfectly. It does not tell you what pulls the trigger. Picture a spinning roulette wheel that is somehow every number at once while it spins, a blur of all possibilities. Then it stops and lands on a single number. The strange physics can tell you the exact chance of each number coming up. It cannot tell you what counts as the wheel stopping. Is it the ball settling? The croupier seeing it? You realizing you won? The wheel never tells you when the magic happens. For most working scientists, this is fine. They use a simple rule of thumb. When a tiny quantum thing meets a big everyday machine, treat the fog as collapsed and read off the answer. It works flawlessly for getting results. But it is a recipe, not an explanation. It says what to do, while quietly skipping the question of what is truly going on. And that gap has haunted physics for a century. Some of the greatest minds alive have stared into the measurement problem and come away admitting they do not understand it. It is the soft, unfinished center of an otherwise rock-solid theory. The math works. The meaning is missing. This open wound is where the wildest ideas in physics come from, because if you try to actually explain what happens during a measurement, you are forced into strange territory. You start asking whether the watcher matters, whether the world splits, whether anything is truly decided at all. Each attempt to solve the measurement problem leads to a picture of reality stranger than the last. And the first of those pictures is the one that tempts almost everyone the moment they hear about this stuff. It is the idea that you, by looking, create reality, that the universe waits for a conscious mind to glance at it before deciding what to be. It is a thrilling thought. It is also one of the most misunderstood ideas in all of science. Time to separate what scientists actually claim from the story people love to tell. You have probably heard it before. Nothing is real until you look at it. Your mind creates reality just by observing. It is a thrilling idea, and it is mostly a misunderstanding. The confusion comes from that loaded word, observer. In everyday talk, an observer is a person, a conscious mind with eyes and thought. So when people hear that observing a particle changes it, they leap to a magical conclusion. They decide that human awareness has special power over the world, that the universe somehow waits for a person to notice it before it makes up its mind. It is easy to see why this spreads. It feels powerful and mysterious. It hints that you are the center of reality, that your gaze shapes the cosmos. Movies and books love it. It sounds deep at a party. But here is what scientists actually mean by observing. They mean any interaction that pulls information out of the quantum fog. A detector clicks. A particle slams into a screen. A speck of light bounces off an atom. None of that requires a human, or a mind, or eyes. A machine alone, in a sealed room with nobody watching, will collapse the fog just fine. The universe was settling its quantum maybes into facts for billions of years before any creature existed to look. So, the strange physics does not say your thoughts create the world. It says that any physical interaction can turn a maybe into a result. The word observer is a poor, misleading label for what is really just contact between things. Your conscious attention has no special magic. A cold, mindless detector does the exact same job. Picture a security camera in an empty warehouse at night. It records everything, whether or not a guard is watching the screen later. The recording happens through the machine, not through anyone's awareness. The quantum world is similar. The fog collapses when particles interact and information gets locked in, with or without a human in the room. This matters, because the magical version leads people to wild places. They start claiming science proves that the mind controls matter, or that you can reshape reality by thinking hard enough. The experiments say no such thing. They are careful, cold, and done by machines that work the same whether or not anyone is in the building. Now, this does not mean the measurement problem is solved. Far from it. We still cannot say exactly what counts as the interaction that freezes the fog. The mystery from the last chapter is fully alive, but the mystery is about which physical events trigger the collapse, not about whether your soul is sculpting the universe with your eyeballs. So the honest picture is humbler and stranger than the magical one. Reality does not need you. It does not wait for your gaze. It settles its quantum maybes through countless tiny interactions, all the time, everywhere, in the dark, whether or not a single mind is paying attention. And yet the deep puzzle remains. If the fog is real, and every possibility is genuinely there before measurement, then what happens to all the possibilities that do not come true? When the roulette wheel lands on one number, where do the others go? One bold answer says they do not go anywhere. They all happen, every single one, in worlds of their own. What if nothing ever really collapses? What if, every time a particle faces a choice, the entire universe splits, and every outcome comes true in its own branch? This is the many worlds idea, and it is one of the boldest answers to the measurement problem ever offered. It takes the strangeness head-on, by refusing to pick a winner. Here is the thinking. The fog of maybes is real. A particle truly does hold many possibilities at once. The puzzle is why, when you measure, you only ever see one result. The many worlds answer is shocking in its simplicity. You see one result because you split along with the particle. Every possible outcome happens. The universe branches, and a copy of you goes with each branch, each one seeing a different answer and believing it is the only one. So when that quantum roulette wheel stops, it does not really choose a single number. Instead, the world divides. In one branch, it landed on red. In another, black. In another, a different number entirely. Every outcome is real, each playing out in its own version of reality, with its own version of you watching it happen. Stretch that across all of history. Every quantum event, every flicker of every particle, since the beginning of time, has been splitting the universe endlessly. That means a staggering number of parallel worlds branching off every instant. In some, tiny differences. In others, whole histories that went another way. Versions of Earth where you made the other choice, where the coin landed differently, where everything you regret went right. Picture a tree that splits at every branch and at every twig, forever, growing more branches than there are atoms in the sky. You feel like you are walking a single path up the trunk, but you are really splitting at every fork, and a copy of you walks down each new branch, each certain they took the only road. It sounds insane. It belongs in a comic book, and yet many serious scientists take it seriously. For one strange reason, it is clean. It does not require any mysterious moment of collapse. It does not need a special rule about measurement at all. It simply lets the fog be real and never forces it to choose. The weirdness goes away, traded for an unimaginable crowd of parallel worlds. The price is staggering. To avoid the mystery of collapse, you have to swallow a near infinity of unseen universes, copies of everything, splitting without end, forever beyond your reach. You can never visit them. You can never detect them. They are walled off completely, each branch blind to the others. Most people find this far too much to accept. A whole sea of invisible worlds, just to explain a single coin flip. But nobody has proven it wrong, and that is the maddening part. It fits the math. It might be true. You might be one of countless versions of yourself, splitting at this very second, reading these very words down a million branching paths. Many worlds keeps the spooky physics and pays with endless universes. But there is one last escape, a final idea that tries to save Einstein's solid, local world by giving up something far closer to home. It asks you to surrender your own free will, and almost every scientist hates it. There is one last way to keep Einstein's solid, local world. You only have to accept that you never truly make a free choice. Ever. This idea is called superdeterminism, and it is the final hiding place for a universe without spooky action. Remember the rigged choice loophole, the one the starlight and quasars worked so hard to close? Superdeterminism is that loophole pushed to its absolute extreme and taken seriously as a picture of reality. Here is the claim. Everything that happens, down to the smallest twitch, was fixed at the very beginning of the universe. Not just the motion of particles, but your thoughts, your decisions, the exact way a scientist spins a dial. All of it was locked in from the first instant, unfolding like a film that was finished before it ever started playing. If that is true, the spooky results can be explained away. The particles could carry secret cards after all, and the universe could have arranged from the dawn of time, for every scientist to choose exactly the settings that make those cards look spooky. The matching would be a setup written into the cosmos at the start. Einstein's solid, local world survives, but only because the whole experiment was rigged before it began, including the choices of the people running it. Even the ancient starlight would not save you. In this picture, the quasars, the scientists, the particles, and the dials were all threaded together by one master script laid down at the beginning. Free choice never existed. It only feels real. Picture your entire life as a movie that was filmed long ago. You sit in the theater feeling like you are deciding what to do next, but the film is already complete. Every word you will say, every choice you think you are making, is just the next frame, already shot, already fixed. You are watching yourself, mistaking the screen for the steering wheel. Almost every scientist finds this idea unbearable, for a reason that cuts to the bone. If your choices were never free, then science itself falls apart. The whole method depends on being able to freely set up your tests, to ask nature honest, independent questions. If the universe secretly scripts your every move, you can never trust a single experiment again, including the ones that suggested superdeterminism. The idea saws off the branch it sits on, so most researchers reject it. Hard. To them, it costs far too much. To rescue Einstein's comfortable world, you would have to throw out free will and throw out the trustworthiness of every experiment ever done. That is a price almost nobody is willing to pay, even to keep reality feeling solid and sane. Still, like the other escapes, it has not been strictly proven false. It clings to life in the shadows, a strange and unloved possibility, a universe with no spooky action, bought by erasing your freedom to choose. So those are the paths. Accept the spooky link as real, or split into endless worlds, or surrender your free will. Whichever you pick, the simple, solid reality you grew up believing in is gone for good. But while scientists argue about what it all means, engineers have done something far more practical with this weirdness. They stopped asking what entanglement means and started building with it. And the first thing they built may be unbreakable. For thousands of years, every secret code could eventually be cracked. Entanglement may have just ended that, forever. Think about how secrets normally work. You scramble a message with a key, and your friend unscrambles it with the same key. The danger is always in the middle. A spy could copy the message or steal the key while it travels, and you might never know they were listening. Every lock in history has had this weakness. Given enough time and cleverness, a hidden watcher can break in. Entanglement changes the game because of one rule you have already met. You cannot look at a quantum particle without disturbing it. Measuring the fog collapses it, and that means any spy who peeks leaves fingerprints behind. Here is how a quantum lock works. Two people, far apart, share a stream of entangled particles. They use the spooky matching to build a secret key, a long random string that only the two of them know because it comes from the linked results of their own measurements. No copy of that key exists anywhere to be stolen. It is born fresh, on both ends at once, from the particles themselves. Now suppose a spy tries to intercept the particles in the middle. To learn anything, the spy has to measure them, and measuring collapses the fog, scrambling the delicate matching. When the two friends compare a small sample of their results, they will see the damage. The spooky correlation will be broken in a way that can only mean one thing. Someone was listening. The mere act of spying announces itself. Picture a letter sealed in a magic envelope that turns bright red the instant anyone but you opens it. A spy could still tear it open, but the moment they do, the envelope screams that it was opened. You would simply throw that key away and start again, knowing it was compromised. The eavesdropper can never read in secret, because reading is never secret. This is quantum cryptography, and it flips the oldest problem in code making. For all of history, you could never be sure no one was listening. Now, for the first time, the laws of physics themselves stand guard. Not a clever trick that a smarter spy might beat someday, but a wall built from the deep nature of reality. To break it, you would have to break quantum physics. And that is exactly the thing the basement experiment and all its descendants proved you cannot do. The stakes here are enormous. Banks, governments, hospitals, power grids, all of them run on secrets that must stay safe. The codes we use today could be cracked by future machines. Quantum locks promise a kind of security that no future computer can ever break, because the protection does not come from a hard math puzzle. It comes from the universe refusing to let you look without leaving a trace. So the spooky link, once a strange curiosity in a basement, has become a shield, a way to send a secret that physics itself protects. And scientists were not content to do this across a lab or even across a city. They wanted to stretch the quantum lock across an entire country and then beyond. To do that, they did something audacious. They put entanglement on a satellite and fired it down from space. In the year 2016, China launched a satellite with a strange mission: to beam pairs of entangled particles of light down to Earth from hundreds of miles up in space. They named it after an ancient Chinese philosopher, and it became the first of its kind. A spacecraft built to test the spookiest physics there is, not in a lab, but across the open sky, on a scale no one had ever tried. The goal was to crack a stubborn problem. Entanglement is fragile. When you send entangled light through cables or thick air, it gets absorbed and scrambled, and after a couple hundred miles, the link is lost. That makes a ground-based quantum network painfully hard to stretch over long distances. Cables simply leak the magic away, so the team looked up. Most of the air on Earth is packed into a thin layer near the ground. Above that, space is nearly empty. So if you put your source of entangled light in orbit and beam it straight down, the particles only have to punch through that thin layer of air at the very end. The rest of the trip is through clean, empty space, where the fragile link survives far better. The satellite carried a machine that made entangled pairs of light particles. It sent the two partners of each pair down to two different ground stations, far apart on the Earth below. Aiming was brutally hard. Picture trying to shine two laser beams from a fast-moving spacecraft hundreds of miles up and hit two specific telescopes on the ground, each one a tiny target, while everything is racing through space. It is like threading a needle from the roof of a skyscraper, with the needle on the far side of a city. And it worked. The satellite successfully sent entangled particles to two stations on the ground, separated by more than 700 miles, a distance like stretching from one end of a large country to the other. When the stations checked their results, the spooky matching was still there. Entanglement had survived the journey from orbit across hundreds of miles of sky. Bell's ceiling broke again, this time with one partner of each pair born in space. This shattered the old distance limit. On the ground, the link died after a couple hundred miles. From space, it reached across a whole country. The team used it to build a secret quantum key between two faraway cities, protected by the same unbreakable rule. Any spy who peeked would wreck the link and reveal themselves. Picture the future this points to: a web of satellites overhead, raining entangled light onto cities around the world, weaving a global network locked by the laws of physics. Messages no future computer could ever crack, carried on a thread of spooky connection beamed down from orbit. The strange physics that began as a fight between two old men and a lonely experiment in a basement was now circling the planet. The spooky link had gone to space and come back, still spooky, still unbroken. And the same deep weirdness is powering one more machine, perhaps the most important of all, a new kind of computer that runs on entanglement and could one day solve problems that would stump every ordinary machine on Earth, even if you ran them until the end of time. The same spooky link that broke Einstein's world is the secret engine inside the most powerful machine humanity is trying to build, the quantum computer. To see why it matters, look at the machine you are using right now. Every ordinary computer, from your phone to the biggest supercomputer, thinks in bits. A bit is a tiny switch that is either on or off, a 1 or a 0. Everything your devices do, every game, video, and message, is built from billions of these switches flipping between two states, on or off. Nothing in between. A quantum computer throws out that rule. Its switches are quantum, which means each one can sit in the fog of maybes you have come to know. A quantum bit can be on and off at the same time, holding both possibilities at once, until it is measured. That alone is strange. But the real power comes from the spooky link. In a quantum computer, the quantum bits are entangled with one another. They stop being separate switches and become one deeply connected whole, where each bit's fate is woven into all the others. This is where the magic lives. Because they are linked and blurred together, a quantum computer can explore a vast number of possibilities at the same time, like checking countless paths through a maze at once instead of one by one. Picture a giant maze with millions of paths, and only one way through. An ordinary computer must try the paths one after another, walking each dead end and backing out, slow and patient. A quantum computer, using entanglement, can flow through the whole maze at once, with all the paths interfering and cancelling until the right one stands out. For certain problems, that is an almost unimaginable leap in speed. This is why the world's biggest companies and governments are racing to build these machines. A powerful quantum computer could design new medicines by simulating molecules that ordinary computers choke on. It could create new materials, untangle the chemistry of nature, and crack problems that would take a normal computer longer than the age of the universe. The same entanglement that puzzled Einstein could reshape medicine, science, and technology. There is a sharp edge to this, too. Remember those old-fashioned secret codes, the ones that protect banks and governments today? Their safety rests on math problems too hard for normal computers to solve quickly. A strong enough quantum computer could blow through some of those problems, cracking codes the world relies on. That is part of why quantum locks, built from entanglement, suddenly matter so much. The same physics gives us both the ultimate code breaker and the ultimate code. These machines are still young and fragile. The entangled states they depend on are delicate, easily ruined by the smallest disturbance, and keeping them stable is one of the hardest challenges in science. But progress is real and fast. The spooky link, once a question scribbled on paper, is now the beating heart of a technology that could change the shape of the future. From a basement in California to a satellite in orbit to the engine of a new kind of computer, the journey of this one strange idea is staggering. So let us step back, all the way back, and look at the full size of what those 3 Nobel winners actually proved about the universe you live in. Because the final picture is the most humbling of all. Albert Einstein was, by almost any measure, the greatest scientific mind in human history. And on the deepest question of all, the nature of reality itself, he was wrong. Sit with the full weight of that. This was the man who saw that time bends and space curves, who rewrote gravity and light, whose name became another word for genius. When he insisted the world must be solid and local, when he mocked the spooky link as a ghost story, he was using the sharpest mind our species has produced, and the universe still told him no. It told him through a young man in a basement who wanted Einstein to win, and watched his own machine prove the opposite. It told him through a French physicist who outran light to swap his questions in mid-air. It told him through diamonds on a college campus, through telescopes drinking ancient starlight, through quasars blazing at the edge of time. Every test, in every form, across 50 years, gave the same answer. The world is not locally real. Einstein's comfortable reality does not exist. In the year 2022, 3 scientists, John Clauser, Alain Aspect, and Anton Zeilinger, stood and accepted the Nobel Prize in Physics for forcing the universe to confess. Their work took the deepest question humans had ever asked, a question once left to philosophers and dreamers, and turned it into a number on a machine. They asked reality what it truly is, and reality answered, plainly, that it is stranger than our greatest genius could accept. And this is not a story about something far away. You are made of it. Every atom in your body holds no fixed traits until it is measured. Every particle in your hand can link across space in ways that ignore distance. The fog of maybes, the spooky connection, the blurry double life of matter, all of it is the cloth you are cut from. You are a solid-feeling creature built out of pieces that are anything but solid. Picture standing on a beach, certain the sand beneath your feet is firm and ordinary. Then you learn that, looked at closely enough, every grain is a flicker of possibility, settling into solid form only because the world keeps measuring it. Moment after moment, the beach holds you up, and underneath, it is shimmering, with a strangeness you were never built to see. That is the universe the experiments reveal. Solid on the surface, where we live, foggy and connected and impossible underneath, where the truth hides. We walk across the firm crust of reality our whole lives, never feeling the deep weirdness holding us up. It took 50 years, 3 brilliant minds, and machines of staggering care to finally reach down and touch it. The smartest man who ever lived looked at this universe and said it could not be so. He spent his final decades searching for the hidden piece that would make the world normal again. The piece was never there. The world was strange all along, and now, stamped with the highest honor in science, we know it for certain. Reality is not what it seems, and it never was. You live in a universe that has no fixed form until it is seen, woven together by threads that laugh at distance, stranger than Einstein, stranger than common sense, stranger than almost anyone is ready to believe. And you are made of the very same strange and beautiful stuff.